Welcome to the Deep Dive, where we sift through the latest research, articles, and insights to give you the clearest, most engaging understanding of cutting-edge AI. Today, we're plunging into a really fascinating corner of artificial intelligence that, well, often flies under the radar. We frequently talk about AI that can see images or understand text, right? But there's a whole different kind of AI that specializes in seeing something maybe even more fundamental, the connections between things, the relationships, the underlying network. And this is often where the real intelligence in complex systems truly, resides. Our mission today, to take a deep dive into graph neural networks, or GNNs. We'll unpack what they are, how they work their magic, why they're so incredibly powerful for tackling some of the trickiest real-world problems, and where this rapidly evolving field is headed next. Consider this your shortcut to grasping the core insights, the unique challenges, and the profound implications of GNNs. It's specifically tailored to help you, our tech-savvy listener and professional, stay right at the forefront of AI innovation. So yeah, get ready for some serious aha moments as we explore how AI is moving beyond isolated data points to truly understand the forest instead of just the trees.
Yeah, and what's genuinely revolutionary about GNNs, I think, is how they fundamentally change the way AI perceives and processes interconnected information. Think about traditional machine learning models for a moment. They're typically optimized for data that fits neatly into tables or grids, like images, essentially pixel grids, or text, which is basically a sequence of words. These models often analyze data points in isolation, just focusing on individual features. And this isolated view, it creates pretty significant blind spots.
Right, like tunnel vision almost.
Exactly. It's like trying to understand a sprawling city just by looking at individual buildings. You might know a lot about each building's height or color, maybe, but you'd completely miss the roads connecting them, the traffic flow, the neighborhoods, how everything interacts. Traditional models, they only analyze isolated features, never the paths between them. They see the dots, but not the lines connecting them. GNNs overcome this because they make those relationships, those lines, a primary component of their learning. This lets AI reason about collective behavior influence within a system, leading to smarter and, frankly, more trustworthy insights.
Okay, so let's start with the basics then. When we talk about a graph in this context, we're not talking about a bar graph or a pie chart, are we? We mean something different.
That's a great starting point. Yeah, absolutely different. Imagine any system where things are connected. A graph is simply a way to model those things as nodes. You might hear them called entities, and their relationships as edges or connections. So in a social network, people are nodes, friendships are edges. Simple. In a molecule, atoms are nodes, chemical bonds are edges. And you can even attach extra information, features to these nodes, like a person's age or an atom's type, or even to the edges themselves, like, say, the strength of a friendship or the length of a chemical bond.
Got it. And GNNs are specifically designed for this kind of data structure.
Exactly. GNNs are a specialized type of neural network built pretty much from the ground up to operate directly on this graph data. Unlike, say, a convolutional neural network, a CNN, which is perfect for image grids, or a recurrent neural network, an RNN, that's great for sequential text. GNNs take the entire graph as input. They inherently understand the structure, the dots and the lines, not just the isolated dots. They're what we call graph-in, graph-out networks. They're designed to preserve and critically learn from the graph structure itself.
That makes a lot of sense.
Yeah.
But what makes them so fundamentally different from, the CNNs and RNNs we might be more familiar with? Is it just about the input format, or is there more to it?
Oh, it's much more profound than just the input format. The core difference, really, is GNN's ability to natively handle what we call non-Euclidean data. Think of Euclidean data as something that lives in a nice, regular grid or a fixed sequence like an image or a sentence. They have a clear sense of up, down, left, right, or next word.
Okay, very structured.
Very structured, exactly. Graph data, on the other hand, is irregular. It's variable in size, and it's fundamentally unstructured. The number of nodes can change, the connections can change, and there's no inherent order to the nodes that matters. So GNNs don't assume data independence or fixed structures. Instead, they embed relationships and context directly into the learning process. They learn directly from the structure of the graph itself. And this is crucial for consistency. Imagine a social network again. It shouldn't matter if you list John before Jane or Jane before John, right? The network of friendships is the same.
Right, the connections are what count.
Precisely. This is where permutation invariance comes in for the overall graph representation. It means the final output is unaffected by the arbitrary order of the nodes. And for the internal layers, there's something called permutation equivariance, which basically means if you shuffle the input nodes, the output representations for those nodes shuffle in the exact same way. It's all about respecting the underlying structure, not the arbitrary way we might happen to list things out.
That's a great way to put it, respecting the structure. Okay, so given this unique setup, how do GNNs actually learn from all these dynamic connections and features? What's the secret sauce behind their ability to process relationships?
Well, the secret sauce is a really elegant mechanism known as neural message passing. Yeah. It's an iterative process, and you can kind of visualize it as each node in the network chatting with its immediate neighbors.
Chatting, okay, like sending messages back and forth.
Sort of, yeah. Here's how it generally works. First, initialization. Every node starts with an initial feature vector. Think of this as like a digital profile for that node, all the info you have about a person in a social network, or an atom in a molecule. Then comes neighbor aggregation. In each layer of the GNN, every node effectively collects messages, information from its direct neighbors. It uses what we call an aggregate function. This could be something simple like averaging all the neighbors' features, summing them up, or taking the maximum value. But it can also be more sophisticated, like attention-based aggregation. This is where the GNN actually learns to assign different weights to neighbors based on how relevant or important their information seems to be for the central node.
So it pays more attention to important neighbors.
Exactly. And finally, there's the node update. An upstate function then combines this aggregated information from the neighbors with the node's own features from the previous step. This creates a new, updated, and usually richer representation for that node, which then gets passed on to the next layer.
So it's not just a one-and-done process then. This chatting or message passing happens repeatedly through multiple layers.
Precisely.
Yeah.
That's the real power here, multi-hop information spread. Stacking multiple layers of message passing is what allows information to travel farther across the graph. If you have, say, 3 layers of message passing, each node's final embedding, its final representation, will encapsulate information not just from its immediate neighbors, but also from its neighbors' neighbors and their neighbors. So effectively, it's looking at its 3-hop neighborhood.
Wow, okay, so it gets a much wider view.
A much wider, much more contextual view. The result is transformative. Each node's representation becomes incredibly contextual. It's not just a summary of the node itself, but a rich digest of its own features and the surrounding network information. This builds what we call neighborhood-aware representations. And there are key architectures that implement this. You might hear names like Graph Convolutional Networks, GCNs, they're kind of foundational. Then there are Graph Attention Networks, GATs, which use that attention mechanism we mentioned, and GraphSAGE, which is really designed for scalability for huge graphs by efficiently sampling neighborhoods instead of looking at everything. It's like the nodes are getting wiser by listening to their community, not just reflecting on themselves.
That brings us neatly to the core question then.
Yeah.
Why are GNNs such powerhouses when it comes to relational data? What unique advantages do they offer that, traditional AI models just can't match?
It really boils down to their design philosophy, as we've been saying.
Yeah.
They see the lines as well as the dots. Traditional models are effectively blind to the network structure. GNNs are designed specifically to leverage it.
Right, so first you mentioned this explicit relationship modeling.
Exactly. GNNs don't just sort of guess at relationships, they explicitly model them. They capture collaborative signals and structural dependencies. They understand how entities connect, interact, and influence each other. This is just crucial for problems where the interactions are maybe even more important than the individual items themselves. Second, they provide incredible context awareness. As we discussed, right? Each node's representation isn't just about itself, it summarizes its own data and its neighbor's data. This makes the GNN inherently sensitive to network context.
The meaning changes based on the connections.
Precisely. A node's meaning shifts based on who it's connected to. And finally, through that iterative message passing, they enable multi-scale information integration, sometimes called multi-hop analysis. They capture both very local neighborhood patterns and broader global graph structures. This allows for complex multi-hop pathfinding, essentially understanding indirect connections and network effects across the entire system.
So if I'm getting this right, it's about moving from analyzing isolated facts, isolated data points, to really understanding the entire ecosystem of information. It sounds like they're performing a kind of relational reasoning.
That's a perfect way to put it. GNNs go far beyond just simple feature analysis. They learn these powerful embeddings, these low-dimensional vector representations that manage to encapsulate both the intrinsic features of a node and its structural information within the graph. This is the heart of what we call representation learning for graphs. And this capability allows them to uncover hidden patterns, predict outcomes, and make data-driven decisions with unprecedented precision. They do this by revealing insights that are completely invisible to isolated attribute analysis. Plus, because of that permutation invariance property, they're incredibly flexible. They can handle graphs of pretty much any size or shape without getting confused if you just happen to reorder the nodes. They're a really sophisticated generalization of deep learning for the messy, irregular world of graphs.
Okay, this all sounds incredibly powerful in theory, but, where are GNNs making a tangible difference right now? Where can we see them in action, solving actual real-world problems?
Oh, their impact is already pretty transformative across incredibly diverse domains. Let's look at some compelling examples. In social network analysis, right? Users are nodes, relationships are edges. GNNs are key here. They're used for community detection, helping identify those tightly knit groups within social networks. And studies have actually shown like a 20% improvement in how clearly these groups are defined compared to older methods.
Wow.
They also power link prediction. That's basically how platforms suggest new friends or connections to you. And perhaps most critically, they're vital for anomaly detection, tracing unusual interaction patterns to identify things like hidden fraud rings or maybe malicious bot activity in cybersecurity. They can spot that subtle coordination that isolated analysis would totally miss.
That's a huge shift from just looking at individual profiles or accounts. What about in other fields, maybe like science?
Absolutely. Drug discovery and molecular property prediction are, well, they're undergoing a revolution thanks to GNNs. Molecules are natural graphs, right? Atoms are nodes, chemical bonds are edges. So GNNs are used to predict molecular properties like solubility, toxicity, or bioactivity, how effective a drug might be. And they often significantly outperform traditional computational chemistry methods. They're also used for drug-target interaction prediction, figuring out how potential new drugs might interact with proteins or other biological targets in the body. And here's something truly amazing, I think. GNNs are fundamental building blocks in advanced AI programs like Google's DeepMind AlphaFold.
AlphaFold, yeah, the protein folding breakthrough.
Exactly. AlphaFold's massive success relies heavily on GNNs to understand the incredibly complex spatial relationships and interactions within proteins as they fold. It's really foundational stuff. And then there's something almost everyone interacts with daily: recommendation systems.
Ah, yes. Movie recommendations, product suggestions.
Precisely. Here, user item interactions, you watching a movie, you buying a product, can be modeled as graphs, bipartite graphs usually. GNNs enhance collaborative filtering, giving superior performance over older methods like matrix factorization, and they enable incredibly personalized recommendations. They do this by understanding not just your individual preferences, but also how you fit into a larger community of users with similar tastes. And a key application here, maybe a real aha moment for understanding their power, is how GNNs effectively address the infamous cold start problem.
Right, the cold start problem, that's when you have a new user, maybe a new item, and the system has no history, no data, so it doesn't know what to recommend. How do GNNs tackle that?
Exactly that. If a new user joins Netflix, say, or a new movie is added, traditional systems struggle because there's no viewing history for that specific user or movie. But with GNNs, even if a new user has only interacted with a couple of items, the GNN can leverage the graph structure. It sees who else interacted with those same items or what types of items that users connected to through those interactions. It can then propagate information from existing, well-represented nodes users or items with lots of history to infer a reasonable representation, a reasonable embedding for the new cold user or item. This allows for pretty accurate recommendations, even with very sparse initial data, making them far more robust and useful in dynamic environments where new things pop up all the time.
Okay, so GNNs sound incredibly powerful, almost like a magic wand for connected data. But as with any cutting-edge technology, there must be limitations or challenges, right? What are the hurdles researchers and engineers are grappling with?
You're absolutely right. No technology is a silver bullet, and GNNs definitely have their share of, let's say, inherent architectural limitations and practical hurdles. On the architectural limitations front, one major issue people talk about is the over-smoothing problem.
Over-smoothing.
Yeah. As you stack more and more layers of message passing, trying to capture longer-range dependencies, all the node representations can start to become too similar, too average. They kind of lose their individual distinctiveness. It leads to what's called representational collapse, which severely reduces their ability to actually discriminate between different nodes for downstream tasks.
Okay. Too much averaging washes out the details.
Exactly. Another related one is over-squashing. Imagine trying to compress, I don't know, a massive complex family tree into a single small paragraph for each person. You'd inevitably lose a lot of information about distant relatives, right?
For sure.
Similarly, GNNs can suffer from information loss when they compress long-range dependencies information from far across the graph into these fixed-size vector representations. It can sometimes make them insensitive to crucial information from distant but important parts of the graph.
That makes sense. It's like trying to get a message across a huge social network, but the message gets too diluted after too many hops, maybe. What are more practical real-world challenges?
Yeah, plenty of those too. The first big one is simply scalability and computational complexity. Processing very large, real-world graphs, think social networks with billions of users and connections, or massive knowledge graphs, requires enormous computational resources and some very clever engineering to make it feasible. Then there's data imbalance. In many real-world scenarios, certain classes are rare. Think about fraudulent transactions, hopefully. They're rare compared to legitimate ones. Or maybe identifying rare diseases from patient data. If your training data is heavily skewed towards the common case, your GNN might really struggle to correctly identify these rare but often very important events. It just doesn't see enough examples. Noise is another pervasive issue. Real-world data is messy. You might have errors in your labels, that's label noise, or inaccuracies in the graph structure itself, missing or incorrect links, that's structure noise. GNNs need to be robust to this.
And interpretability, is that an issue like with other deep learning models?
Absolutely. Like many deep learning models, GNNs can often be black boxes. This means interpretability is a significant challenge. Understanding why a GNN made a specific prediction, why it recommended this product, or flagged this transaction as fraudulent, or predicted this molecule property can be really difficult. And that's a major concern in high-stakes applications like drug discovery or finance, where you really need to be able to trust and justify the decisions. And finally, just the task of data preprocessing and graph construction can be surprisingly tricky. Building the right graph structure from raw data, deciding what the nodes and edges should even be, especially for dynamic systems that change over time, is often more art than science right now.
Okay, so despite these hurdles, it sounds like the field of GNNs is clearly exploding with research and development. What does the road ahead look like for these powerful networks? Where is the research heading?
Oh, the future is incredibly exciting. Researchers are constantly developing improved architectures specifically designed to tackle issues like over-smoothing and over-squashing, really pushing the boundaries of what GNNs can effectively learn and represent. There's also a huge focus on scalability solutions. How do we handle truly massive web-scale graphs? People are exploring techniques like graph sparsification, simplifying the graph, and sophisticated parallel and distributed computing approaches. Enhancing model interpretability is also a major research thrust, as we just discussed. There's a lot of work going into developing methods that provide clearer insights into GNN decisions, which is absolutely critical for building trust and enabling wider adoption, especially in sensitive domains.
Are they being combined with other AI techniques?
Yes, absolutely. We're seeing fascinating integrations with other AI techniques. Imagine GNNs working alongside reinforcement learning to optimize traffic flow in a city graph, or maybe with generative models to design entirely new molecules with desired properties, or even using GNNs together with large language models to reason more effectively over structured knowledge graphs. This fusion could unlock entirely new capabilities. Furthermore, handling dynamic and heterogeneous graphs, graphs that change structure or features over time, or graphs that contain different types of nodes and edges, maybe multimodal data is a rapidly growing and important area. And finally, on a more theoretical level, researchers are working hard to establish stronger theoretical guarantees for when and why GNNs generalize well, which will build even greater confidence in using these powerful models reliably.
Well, we've certainly taken a deep dive into graph neural networks today, a really revolutionary part of AI that is fundamentally changing how we process and understand interconnected information. You've seen how GNNs are often quietly essential for everything from recommending your next favorite show to helping design potentially life-saving drugs. The world around us is increasingly interconnected, isn't it? And the ability to understand and leverage this relational data is only growing in importance. GNNs are truly at the forefront of this evolution, and they seem poised to drive even more groundbreaking discoveries in the years to come.
Yeah, and that leads to a final thought, perhaps, for you, our listener. Given GNN's remarkable power to uncover these hidden relationships and patterns, what complex network or system in your professional field, or maybe even just a personal interest, do you think could be transformed by finally seeing the lines as well as the dots? Something to ponder.
Definitely something to ponder. That's it for this deep dive. If you found these insights valuable and want to stay well informed on the cutting edge of AI, make sure to subscribe to the Before AGI podcast for more in-depth content like this. And for those of you who want to go even deeper, maybe get your hands dirty with practical tutorials and more hands-on insights, be sure to check out Ian Ochieng, that's Ochiengai, on YouTube. We'll be back soon with another fascinating topic. Thanks for tuning in.